Lesson 33, finding the probability of independent and dependent events. Here in our new concepts, we're going to define independent and dependent events and then work to practice through our first example on identifying the different type of event that's happening in order to calculate probability. In example 2, we're going to use a tree diagram to see how those things work in progression. Example 3, we're going to calculate probability of dependent events. And then in example 4, we're going to calculate odds. In example 5, we're going to solve multi-step problems involving probability. We'll wrap it up by looking at our lesson practice, so it'll hopefully help you with your assignment. Our new concepts says events where the outcome of one does not affect the probability of the other event are called independent events. That means they happen by themselves. To find the probability of two independent events, multiply probabilities of those two events. For example, spinning a spinner and flipping a coin are independent events. You spin it one time, it happens one time by itself. Flip a coin happens one time by itself, they're independent. The result of one does not affect the result of the other. What is the probability of spinning a 3 and landing on heads? Well, you have to take probability into account in terms of the total number of outcomes versus the desired outcome. So you're looking for a 3 in terms of 1, 2, 3, 4, 5. So a 3 is 1 out of those 5 possible landing spots. Flipping a coin is 1 out of 2. If you're looking for heads, there's 2 sides to a coin. It's 1 out of 2. So you have those 2 independent probabilities. To find those probabilities together, you're going to multiply those two things. 1/5 times 1/2. You multiply the denominators and the numerators. 1 times 1 is 1 in the numerator. 5 times 2 is 10 in the denominator. So you get the independent probability of those two independent events. Spinning the spinner twice also creates two independent events. The first spin does not affect the second spin because they happen by themselves. What is the probability of spinning a 5 and spinning a 1? So you've got 1/5 probability for getting a 5 and 1/5 probability for getting a 1. You multiply. 1/5 times 1/5 is 1/25 because they're happening independently. Here's the difference. With dependent events, the outcome of one event does affect the probability of the other event. To find the probability of two dependent events, you multiply the probability of the first event by the probability of the second event. So the math is still the same, but you have to think dependent events have this connection between what happened in the first event and what happened in the second event. So the second event is based on or given the results of that first event. Here's an example that's written out. Independent events, the outcome of the first event does not affect the second event, so you've got two probabilities, one's being multiplied by the other. In a dependent event, the outcome of the first event does affect the second event, where the second event's probability is calculated under new conditions. For example, if I've got 5 marbles in a bag, 3 of them are green, 2 of them are gold, and I want to figure out my probability of picking one marble out. So I've got a 1 in 3 chance, or sorry, a 1 in 5 chance of picking a marble, and 3 of those are going to be green, so 3 out of 5 of getting a green, 2 out of 5 of getting a gold. If I pull one out and I leave it out of the bag, now I only have 4 marbles in the bag. The probability of the second event there is different, so my new probabilities would be something out of 4 because I've got a dependent event. It happened in a row or happened one after the other. There's a second event that is depending on the first event that happened. We'll see that in a couple of our examples. Example 1, let's identify situations involving independent and dependent events. Here we're going to take the easy way out. We'll just look at the solution that's given us and help that give us our understanding. Letter A, rolling a 6 on a number cube and a 4 on another number cube. This is an independent event because rolling one number does not affect the outcome of rolling the other. Rolling a 6 on a 6-sided die or a number cube is 1 out of 6. Rolling a 4 is 1 out of 6. My two probabilities would then be multiplied. 1/6 times 1/6 would give me 1/36 if I wanted to calculate the independent events of those two separate events. Letter B, rolling a 6 on a number cube and then a 4 on the same number cube. These events are also independent because when I rolled the dice, I can just pick it up and roll it again. It doesn't have an effect on what the previous roll was. So this again has the same probability. Just because I'm using the same cube doesn't change anything. Letter C, drawing a red marble from the bag, keeping it out of the bag, and then drawing a blue marble. Now these events are dependent because I didn't replace the first marble. The total number of marbles in the bag have changed, and that second draw is going to be affected by that. There are fewer marbles to actually choose from. Letter D, drawing a red marble from a bag, putting it back in, and then drawing another blue marble. These events are independent. Because I restored the total number of marbles, I have the same probability calculations that I would if I started in the first place. If I've changed something in the course of calculating the probability, that's where the dependent event comes in. So this is independent because you get the same probability. The first event doesn't affect the second event. So in example 2, we'll look at a tree diagram. This can help demonstrate sample space for different events. Using a tree diagram, A coin is flipped twice. Make a tree diagram showing all possible outcomes. What is the probability of the coin landing on heads both times? So in this example, you want to consider this as a dependent event because the first outcome and the second outcome are tied together. You want to put these things in order. So you're calculating independent probability by multiplying those two things together. To get a heads and a tails, you've got 1 out of 2 and 1 out of 2. And then you've got a possible heads in the second flip, you've got a heads or a tails. Second flip, you've got a heads or a tails if you got a tails the first time. So here's your outcome. Head, head, heads, tails, tails, heads, or tails, tails. What's the probability of getting a heads both times? Well, you've got a 1.5 chance here, and then you got a 1.5 chance here. 1/2 times 1/2 is going to be 1/4. So this kind of shows you what that looks like. This would be 1 out of 1, 2, 3, and 4 of those outcomes. This is just a visual of what that probability actually looks like. Example 3. Let's calculate the probability of dependent events. Remember, dependent events are events that matter to what happened in the first event. For example, Natalie has 2 squares and 3 circles in a bag. Find the probability of drawing a circle, keeping it, and then drawing another circle without the use of a tree diagram. For the first, draw the bag and then draw 5 shapes. 3 are circles, 2 are squares. For the second draw, a circle has been removed. There is 1 less circle and 1 less shape. So in the first example, the first circle, you've got 3 out of 5 are circles. However, when you've taken 1 out, one of the circles has been removed. Now you only have a total of 4 shapes, and 2 of them are circles because you took one of the circles out. So you got 3/5 times 2/4. If you multiply those together, 3 times 2 is 6. 5 times 4 is 20. You can reduce that to 3/10. Because the two events are dependent, the first event matters to the second event because it changes the second event. You've got 5 things to choose from. Now you've got 4 things to choose from. In letter B, find the probability of drawing a square, keeping it, and then drawing a circle. Same scenario. You've got a bag that has 5 shapes. In those shapes, 2 of them are squares, 3 of them are circles. So let's figure out the probability for a square. Notice how they put this little parenthesis here and it tells you what you're looking for. 2 of the 5 are squares, so you get a probability of 2 out of 5. The 2 is the desired outcome over the total, so 2 out of 5. The second time that you're pulling something out, you have removed one of those squares. So your total of shapes is not 5 anymore, it's 4. But you still have the same number of circles. In this one, it says for the second draw, square has been removed. There's 1 less shape, but the number of circles is the same. Circles was 3 out of 5 to start. Now there's only 4 shapes, so it's 3 out of 4. Then you're going to calculate, because it's a dependent event, by multiplying these two things together. 2/5 times 3/4. 2 times 3 is 6. 5 times 4 is 20. And you get a probability of 3/10 by reducing again. So in both of these examples, your dependent events, you've got a first event that's happening, then something changes. Notice your new probability is different because it's got a different denominator, different total outcomes, because one of those things has most likely been removed. The math is the same because you're calculating by multiplying both of those things in the first event and the second event together. Odds. Bottom of page 206. Odds are another way of describing the likelihood of an event. Odds are expressed as a ratio, so a comparison between the likelihood of an event or the opposite of something happening. Odds are expressed as a ratio, usually written with a colon. Odds can be calculated by something or against something happening. Here's the definition of odds. Odds of an event is a ratio expressing the likelihood of an event. Assume that all outcomes are equally likely. There are favorable outcomes or unfavorable outcomes. Another way of saying that, there's something that you want to happen versus what you don't want to happen. So the odds are a comparison of M, the favorable outcomes, versus N, the unfavorable outcomes. In example 4, we're going to practice calculating odds. Here's an example. A bag contains 6 red marbles, 2 yellow marbles, 1 blue marble. So count those totals. You got 6 plus 2 is 8 plus 1 is 9. A total of 9 if you're calculating probability. But we're not calculating probability, we're calculating odds. Odds are favorable outcomes versus unfavorable outcomes. So you got to kind of shift your thinking. The question in letter A says, what are the odds of drawing a red marble? Well, red would be our favorable outcomes, and then the other colors would be unfavorable outcomes. So I'm not comparing 6 to 9 as I would in probability. I'm comparing 6 to 3 because 6 are red and 3, 2 plus 1, are not red. So in this example, 6 compared to 3 would be our comparison. Here's our odds, 6 out of 3. If you reduce that, because both those are divisible by 3, it's actually 2 out of 1, or 2 compared to 1, as how you would calculate odds. Notice it's not a fraction, it's a colon, or an expression of those comparisons with those numbers right here. Letter B, what are the odds against drawing a blue marble? What are our favorable outcomes versus unfavorable outcomes? Now notice the language here. It says, what are the odds against drawing a blue marble? So look at the favorable outcomes and the unfavorable outcomes. There are 8 marbles that are not blue. Not blue would be 6 plus 2 is 8. So 8 of those are unfavorable outcomes. Drawing a blue marble is 1, so I'm going to compare 8 to 1 as my odds. You don't have very favorable odds in terms of drawing a blue, but you have a high favorable odds in terms of drawing something that's not blue. So you have to pay attention to what the language says in that question when it's asking you to calculate odds. Example 5, solving multi-step problems involving probability. Isaac has 6 blue and 4 white shirts in his closet. There are also 2 pairs of navy pants and 3 pairs of khaki pants in his closet. What's the probability Isaac will choose a khaki pant and a white shirt from his closet? Well, to calculate probability in this example, you have to consider what you have for a total of pants and what you have for a total of shirts. In terms of pants, he's got 2 pairs of navy and 3 pairs of khaki, so he's got a total of 5. 3 out of those 5 are khaki, so here's your probability. In terms of calculating a white shirt, you've got 4 out of 10, which is reduced to 2/5. To find that probability, you multiply those two together. 3/5 times 2/5 equals 3 times 2 is 6, 5 times 5 is 25. Here's your calculation for those specific categories. Notice the probability is put into those categories based on the comparisons of those things. And letter B, it said assume that after the pants and shirt are worn, they are put in the laundry hamper. What's the probability that you will choose khaki pants and a white shirt from the closet to wear the next day? Well, now you've got to change things because they're in the hamper. You've got a different total that's in the closet. Notice the khaki pants went from 3 out of 5 to 2 out of 4 because you lost both one of those probabilities and the total. And your white shirts went from 4 out of 10 to 3 out of 9, so you've got a new probability the second time. You'd multiply those two things together, 1/2 over 1/3 after you reduce those, and you'd get 1 out of 6 the second day. Let's take a look at our lesson practice so you can see some of these examples that might match up with what you have in your homework assignment. In the first section, A, B, C, D, and E, it says identify each as independent or dependent. Letter A, a card is chosen from a deck of cards replaced and the second card is chosen. Because that card was replaced, you still have the same probability, therefore this is an independent event. The first event doesn't affect the second event. Letter B, a marble is drawn from a bag, kept, and then the second marble is drawn. This is dependent, dead giveaway, because you changed the total of marbles in the bag. Letter C, a coin is flipped and then a number cube is rolled. This would be independent because they do not affect each other. They're both by themselves happening. Letter D, a spinner is spun and the result is recorded. Then the spinner is spun a second time. Again, this is independent because the spinner spinning to one spot doesn't mean anything's removed or changed. You still have the same probability as it goes around because it's happening as an independent event. It's all by itself. It's independent. Letter E, a coin is flipped and a 6-sided number cube is tossed. Make a tree diagram showing all possible outcomes. What are the probability of landing on tails or on an even number? In this case, in terms of flipping a heads or a tails, you've got 1/2 as your probability. And then the second outcome is having it land as tails or an even number. Your even numbers are going to be 2, 4, and 6. So you again have 1/2 of happening of those 6 times, so 3 out of 6. So you multiply those two things together. 1/2 times 1/2 is going to equal 1/4. In the next section, it says a bag contains 4 red blocks and 3 blue blocks. It says in letter F, find the probability, and letter G, find the probability. So let's practice. Find the probability of drawing a red block, keeping it, and then drawing another red block. So red blocks would be 4 out of 7 the first time. You got that red block out, and now you have 3 out of 6, so you'd multiply those two things together, 4 out of 6 and 3 out of 6. When you're multiplying, you then reduce, you're going to have your final probability. That final probability is going to be 2 out of 7 once you've reduced both of those multipliers. In letter G, find the probability of drawing a blue block, keeping it, and then drawing a red block. If you're going to draw a blue block, the first time you've got 3 out of 7 that's being multiplied. Then you're going to keep that and draw a red block, which is 4 out of 6, so a higher probability. You multiply those two things together, and you find your dependent probability of that event. In this last section, you're going to use the spinner for H and I. It says, what are the odds of spinning black? Well, odds would be favorable versus unfavorable, so we count the number of black, 1, 2, and we count the number of non-favorable, 1, 2, 3, 4, 5, 6. So I'd have 2 compared to 6. Those can be reduced. 1 out of 3 would be my odds of spinning black. Letter I, what are the odds of spinning gray? So count the favorable, 1, 2, 3. Count the non-favorable, 1, 2, 3, 4, 5. So 3 to 5 would be my odds of spinning gray. In the last portion, it asks you to think about campers that select 1 inside activity and 1 outside activity daily. There are 5 inside activities and 8 outside activities. Letter J says, what is the probability of choosing pottery and horseback riding on the first day? Well, pottery is your inside activity, so that's 1 out of 5, and horseback riding is 1 out of 8. You multiply 1 out of 8 times 1 out of 5, you get 1 out of 40. Letter K, inside activities can be repeated, but outside activities cannot be repeated. What is the probability of choosing pottery and swimming the second day? Because that second one can't be repeated, it changes the probability for outside events. So inside events, you still have 1 out of 5. Your outside event is then 1 out of 7. 1/5 times 1/7 is 1/35. Hopefully those example problems help you with completing your lesson practice problems. God's blessings.